Hello, welcome to Networkers Champ YouTube channel. My name is Abhi, and based on the request, many people have requested to publish the video on STP switching environment. So here we go. This basically video covers all questions related to spanning tree protocol. So, for example, how STP prevents loop, how root bridge is selected in STP and its functions, what are STP states, and there are definitely a follow-up question, right? So this basically completely interview-based questions and answers. And if someone is preparing for interview, these questions will help them a lot to clear because this is based on the real-time interview questions and how we basically answer, right? So beside these topics, there would be a follow-up questions as well that usually interviewer would ask, right, from the candidates. And a proper answer as well, I have listed down, and this is what we are going to walk you through. Let's get started with the first question. How STP prevents loop, right? Now, these questions and answers, you cannot actually mug it up, right? You need to basically build a very strong foundation, isn't it? So you should know first what is prevent actually, what is loop, right? You should know first what is loop, and then you would get to know, you would understand how STP prevents it. So what is loop? That's the first question. But even before that, right? Let's see the communication, how the communication takes place between this PC1 and PC2. I have here PC1 that wants to communicate with PC2. Maybe let's say you are sending an ICMP packet, ping, or maybe you're sending data or email, whatever, right? But the first thing what happens is this. Why? Because when it comes to the forwarding mechanism, right? Let's say ping, right? So when you ping PC2, right, what is the first thing happens? It checks the source IP, destination IP. It goes through the OSI model. And as we all are aware of, ping works at layer 3. So means there would be source IP and destination IP. So source IP would be PC1 and destination IP would be PC2. And then it will be handed over to the data link layer, right? Data link layer means Ethernet header. In Ethernet header, we have source MAC and destination MAC, right? So this source MAC, since this computer knows, the PC1 knows what is the MAC address of itself, right? But it doesn't know what is the destination MAC. Why? Because maybe they are communicating first time in the network. So if they're communicating, they would not be knowing what is the MAC address of PC2. Let's say PC1 is the MAC, PC2 is the MAC of PC2, right? So what basically, in order to, now it cannot be incomplete also. I'm talking about the layer 2, right? Layer 2, it cannot be incomplete also. Source MAC and destination MAC has to be there. So in this case, source MAC is, let's say, PC1. But what about destination MAC? Since it doesn't know what is the destination MAC, this is where it would use 12 times FF, right? That basically is the L2 broadcast address, right? Why? Because PC1 doesn't know the MAC address of PC2, and this is where PC1 will use ARP to learn the MAC address of PC2. How ARP basically flow works? PC1 is going to generate layer 2 as well as layer 3, right? There would be layer 3 as well, where you'll have source IP and destination IP, by the way. So source IP, as we all know, it is going to be what? Whatever, let's say 0.1 and then destination IP 0.2. Consider this is 0.1, 0.2, they are in the same network, right? So that's basically the layer 3, and then this is layer 2. And this information basically would be broadcasted, okay, to switch 1. Now, how switch basically behaves? Switch has a three function of, right? Address learning, address forwarding, and address and preventing loop. So address learning switch will open a layer 2 header, right? We'll check what is the source MAC PC1. And this basically, anyways, this whole process I have, explained it beautifully in other videos. Please do subscribe and like this channel so that you get all related videos directly to you, right? So switch one basically would look at the destination MAC and forward it on this interface, F0/2. Switch 2 receives it, and finally switch 2 would send it to PC2. PC2 would reply ARP reply with its own MAC address, and that is how basically the PC1 gets the MAC address of PC2, right? But in this process, in this basically overall flow, did we see any loop? No. But there is a challenge here. Let's say hypothetical situation. What if this particular interface is down? Then obviously the communication between this segment and this segment would be broken. Now, how would you resolve it? Maybe what you do that, okay, why don't we use a redundant interfaces here? So I would add one more interface. And let's say this is F0/3, F0/3, and this is also same F0/3, right? As soon as you add the interface, let's again understand the same flow. Let's again go through it, right? So PC1 sends the R broadcast, switch 1 receives it. Switch 1 would broadcast it here as well as here, right? On this interface as well as on this interface. When switch 2 receives that R broadcast on switch 0 F0/2 interface, it will broadcast it here as well as it will broadcast it here. When switch 2 receives the broadcast or broadcast from on F0/3, it will again send it here as well as over here, right? Same. So, okay, PC2 receives it, maybe PC2 would reply, right? But this message what switch 1 received, this message on F0/2 would be broadcasted here as well as here. What switch 1 has received on F0/3 would be broadcasted back here as well as here. So what is happening here? These kind of ARP broadcast messages are looping around or moving around the network without any, stoppage. Multiple copies are sent to the machines, multiple copies are sent to the machines, and these informations, this basically information will keep moving between switch 1 and switch 2, and if there are other switches also, they lead there as well. This is called loop, and it is dangerous because it can choke all the bandwidth of the interface. It can basically utilize the resources of all the devices. Ultimately, your network can become unstable, right? So this is where, to prevent the loop, that's where, right? So what STP does, STP actually comes to the picture in this case where we have redundant links, right? And it basically prevents the loop. How it prevents the loop? STP prevents loop by selecting one switch as a root bridge and putting some ports in forwarding state and some ports in blocking state, right? Based on the selection process. So what happens basically? STP is by default enabled, by the way, right? So what STP, as soon as we have redundant link, even though I don't have redundant link, but also switch, basically one of the switch will become root bridge. Okay, now the question is, whosoever becomes root bridge, and then STP will also see, instead of forwarding all the two ports, they would put into blocking state as well as forwarding state based on the selection process. Now, just now I mentioned that STP will select a root bridge out of all the switches. Now, how root bridge is selected? That's the another follow-up question that they may ask. How root bridge is selected? So the root bridge is selected based on the lowest bridge ID. As soon as we answer, there may be a follow-up question again. What is bridge ID? right? So bridge ID is the combination of bridge priority, right? So total, the length of bridge ID is 8 bytes, where the bridge priority is 2 bytes. The combination of bridge priority, the default bridge priority is 32768, and then the MAC address, which is 6 bytes. 6 plus 2, 8 bytes, right? Now, because the default priority is same on all the switches, 32768, right? This selection basically happens based on the lowest MAC address. So if the bridge priority is the same across all switches, the lowest MAC address is used to consider lowest bridge ID. So let's say switch 1 is the MAC of switch 1, switch 2 is the MAC of switch 2, right? And because the priority is same 32768, same here, which switch has the lowest bridge ID? The lowest MAC is switch 1. So switch 1 would become the bridge ID, the lowest bridge ID. Hence, switch 1 becomes root bridge. STP selects it automatically. Switch 1 becomes the root bridge. And then switch 2 and other switches becomes non-root bridge. Another follow-up question may be how bridge ID is exchanged? Or in other words, how switch 1 knows what is the bridge ID of switch 2 and switch 2 knows the bridge ID of switch 1? How do they know each other's bridge ID, right? And this is where the answer is switches use BPDU to communicate with other switch, which is sent in every 2 seconds. And BPDU carries all information, which is true, right? This switch will generate a BPDU. This switch will generate a BPDU, right? In that BPDU, that basically BPDU carries the switch one information, like what are the, what is the bridge ID, what is the version, what is the BPDU type, right? What is the max edge forward time, all that details, it is there in the BPDU, inside of BPDU. So when both exchanges actually BPDU, they get to know each other's bridge ID as well. Now, there may be here a follow-up question again. If switch 1 sends a BPDU, let's say on F0/2 and F0/3, what would be layer 2 as a source MAC and destination MAC? Or what would be source address and destination address? That's where I have mentioned here follow-up questions. What would be source and destination address to send BPDU? So the source address would be sender switch interface MAC address. Means the source MAC would be if the BPDUs are generated on this interface F0/2, the source MAC would be this interface MAC address. The destination MAC address always is a multicast address 0180C20000. That's very important question, and they may ask this follow-up question pertaining to BPDU. Right? So that is the answer. Now you guys can always pause the video, go through it if you don't understand anything, right? We have a YouTube channel, as you are aware of. You can put it there and we will reply. Okay. Another question, types of BPDUs. So you can say the follow-up question, or you can say another question, that what are the types of BPDU? So there are two types of BPDU. The one is called configuration BPDU, right? And it is used for spanning tree computation. This configuration BPDU is sent by only the root bridge. Just remember that. Okay. And then the second BPDU is topology change notification, which is TCN BPDU, which is used to announce changes in the network topologies. As whenever there is a change in the network, the non-root bridge will send a TCN BPDU, right? And then root bridge will actually turn that flag, TCN flag, on and send it across. So these are the answer is these are the two types of BPDUs. Another question they may ask, what are the STP states, right? So we have disable states. Disable is when the port is shut down actually. We have blocking state. Blocking means as soon as you no shut down that interface, unshut that interface, switch blocks that port immediately in order to prevent the loop. Okay, so that a port cannot receive. So be blocking, what you can expect on the blocking. A port cannot receive or transmit data and cannot add MAC addresses to its address table. Means instead a port is allowed to receive only BPD. So the port which is blocking state cannot send and receive data, and it cannot also send BPDU but only can receive BPDU. That's the blocking. Next state is listening. Listening means the port again cannot send and receive data frames here. However, the port is allowed to receive and send the BPDUs. That's the difference. In listening state, it can send the BPDU now as well as receive the BPDU. In learning state, the port cannot yet send any data frames, only can receive and send BPDU, and this is the state where the learning happens, as in who should be, root bridge, who should be non-root bridge, what would be the port roles. This is what it happens. And after the decision is made, finally the port would be in forwarding state. Means the port can send and receive data frames and send and receive BPDUs. Right? That's the answer of this question. They may ask, what does blocking means? What does listening means? Maybe a follow-up question here, how long they spent, right, in each state. So listening state, basically 15 seconds, learning states 15 seconds, right? And forward delay is 20 seconds. Another question, how STP ports are selected? What does that mean? So as you all are aware of, there are three port roles, right? Three port roles. Let me put it here. Um, Port roles. One DP, which is designated forwarding, or you can say forwarding itself. The second is a root port, which is a root port, RP. And then third, blocking port, right? So designated port or forwarding, both are same actually, forwarding, right? These are the three port roles usually in the switch interface. Now, the question is how STP ports are selected, right? So STP ports are selected based on the below sequence. There is a sequence condition of, sequence actually that it goes through. So first of all, the switch which is a root bridge, in this case switch 1, all port would become designated port, and this is where the lowest root bridge ID will have the DP port. Means who is the lowest bridge ID here on this switch, these two switches? Switch 1. So all port would be DP. This port would be DP and this port would be DP. And this would be forwarding. Just remember, STP only works within the connection between the switches, right? Because there is no BPD received on this interface. This basically interface is not the part of STP. It is enabled, but that's another thing, right? So here, both the ports become DP. Now, switch 2 cannot port either of the port as a DP because DP is already selected at the remote end, right? This is where the second basically, now what are the port roles left? RP is left here and blocking. So to select RP now, it goes to further lowest route path cost to the root bridge. Path cost, as you all are aware of, there are defined path cost. If it is fast Ethernet 100 Mbps, 19 is the cost. For gig interfaces, cost is 2, like that. So since here it is fast Ethernet 100, both has the 19 cost and 19 cost here. So it would not select none of the port based on this path cost. But yes, if let's say this is gigabit interface where the path cost is 2, if this is fast Ethernet, this would become straight away RP here. This would become RP. But because this is the cost is here same, because interface type is same, it will go to the next, which is lowest sender bridge ID. Now, lowest sender bridge ID, this is the sender, switch 1 is the sender. It is sending the BPDU on this interface, and this interface, the BPDU would remain, bridge ID would remain same. So this also would be skipped. Next is lowest sender port priority. By default, the port priority is 128. Here we have 128, here we have 128, that you can change again. So if it is default, then switch 2 would not select any of the port as a root port. But yes, you can fine tune, change the priority here, right? If you want this port to be root port, you can change it. But let's talk about the default. This also would be skipped. The final is the sender lowest port ID. Port ID means the interface ID. Who is sender? Switch 1 is the sender. Which interface is the lowest here on switch 1? F0/2. So F0/2 means this interface leads to here F0/2. This would become root port. Now because root port is selected, they are already DP here. Let me put it here just for your convenience. This is DP. This is RP. Now what is left? There would be one RP, by the way, within the switch. So what is left is blocking. So this port would automatically blocked. So any communication now between PC1 and PC2, which port will take? This port or this port? The answer is this port, F0/2. Switch 1 would send it here as well as, but switch 2 would not receive that frame on F0/3 because this is blocking, and we know in blocking what happens? A port cannot receive or transmit data. Switch 2 will still receive BPD on this blocking port. So if let's say actual RP goes down, right? Switch 2 will turn this port from blocking to listening, learning, and finally this will become RP. Right? So it is important to clear your doubts. It is all about the conceptuals, right? So you need to clear your doubts, have a very good concepts understanding, right? Okay. Another question, what is the difference between STP and RSTP? That's very common question that the interviewer asks actually, STP and RSTP. Right. So STP, RSTP basically is called Rapid Spanning Tree Protocol, and as name says, rapid, right? This is where the main difference is that RSTP converges much faster than STP due to more efficient proposal and agreement process because RSTP has proposal and agreement process. And on top of in RSTP, each switch can generate the configuration BPDU. In STP only, who can generate the BPDU? Root bridge. But in RSTP, each switch can generate the root bridge BPDU, sorry, can generate the BPDU, right? But then new port roles in RSTP, we have only, three port roles, which are actually um, learning. So basically blocking, disable blocking and listening, that is into the discarded state, right? And then we have learning and forwarding. You have also alternate and backup. So discarded means alternate and backup, isn't it? So this alternate and backup, same similar to STP only, but instead of blocking that port, there would be also a alternate port, or we can call it backup port. And the ability to quickly flush MAC address and table entries when a topology change occurs. How it works in STP? STP can take up to 50 seconds, right, to converge overall traffic after a link fails. But in STP, it can be done within the 10 seconds because of the rapid response in rapid spanning tree protocol. Right. So again, you should know the concept before actually answering this question. So if you don't know, please, there are videos that I have uploaded which basically talks about all the process. Another question, They usually ask what will happen if in two switches STP is running and in two other switches RSTP is running. Let's say there are total four switches. Two switches STP is running and two switches RSTP. Would that communication take place? Yes, they can interoperate. But basically, RSTP will fall back to STP. So if a network has a mix of switches running classic STP and RSTP, all switches will operate under the slower STP rules, right? RSTP is backward compatible and will communicate with STP switches using the older STP protocol. So like how STP works, right? You would not get actually the RSTP features like the faster convergence, what we just now discussed here. You will not get all those features and it will work. All four switches will work as a old STP. Okay. Now there are different types of STPs. We have CST, we have PVST, PVST plus, rapid PVST, RSTP, which is right. So I hope you guys are aware of all those different types of spanning tree protocol and their functionality. Okay. So with this, pretty much I have covered everything and thank you for watching. Please do subscribe and like, the video so that the next video when we upload, it should reach you. Thank you for watching. Have a nice day. Take care.